Hello everyone, my name is Ze Zhang. My PhD is about multi-sensor fusion for in-process monitoring of electrical machine manufacturing. This presentation consists of the following parts. Firstly, the background and current process monitoring studies in EM production will be introduced, and then the aims and objectives of this project. Finally, the current achievement and the future plan will be explained. Let's start with the background. Electric machine becomes more and more important as the environmental problems are becoming serious. The long-term solution will be the all-electric society, and the EM is considered the best solution. Currently, EM are widely used based on the investigation did by ABB company. It contributes to 28% of global electricity consumption and its demand is growing rapidly. So, EM manufacturing is getting a lot of attention now. EM production is a complex process with a long production line. The overall manufacturing process is shown in this figure. The single metal sheet is stacked to make the laminated core. Then, the electric wire is wounded on the laminated core, which is called the wounding process. After assembly with shaft, housing, and some accessories, a EM is finished. Since the winding process has a very broad impact on product quality, and there are few existing in-process monitoring solutions, the winding process is chosen as my research topic. The main goal of this process is making the coil with even wear profile without wear damage. However, due to the highly non-deterministic nature of the winding process, the following faults are inevitable, which are geometry faults, fault resistance, and wear damage. The quality assurance highly depends on the end-of-line test, which is labor-intensive and time-consuming. To improve this process, there have been some studies. Current research can be divided into several main aspects. They are control-related, simulation, and fault inspection. This work built a foundation for process monitoring, as the nature of this process is well researched. However, no matter how well the design of the winding process, faults are inevitable. The research on fault inspections is relatively rare. Currently, the end-of-line test is still necessary due to the insufficient in-process traceability, which requires a lot of time. Multi-sensor fusion is considered a possible solution here. This is because, firstly, the accuracy of single parameter inspection is not sufficient to replace the end-of-line test. Secondly, single fault inspection is insufficient, and multiple types of fault inspection requires a variety of in-process parameters. Finally, one type of fault in this process may be caused by several in-process parameters. So, here comes to the aim and objectives. The overall aim of this project is to develop a multi-sensor inspection framework to improve the traceability of EM production. By sensorizing the key production process and analyzing the in-process data, the product can be inspected while it's being manufactured, thus eliminating the need for the end-of-line tests to some extent. There are three specific objectives. The first one is develop a multi-sensor fusion framework for capturing spatial-temporal failures in the winding process. There are some challenges here. At first, building an accurate model for this process is very difficult, and the in-process data have differences in physical units of measurement, sampling resolution, and spatial-temporal alignment. It is difficult to synchronize and normalize the sensors with different working modes. Then, how to establish a unified feature representation and association relationship for different types of data should be addressed. Finally, the noisy environment makes this task more difficult. The second objective is further develop this inspection framework for multi-false type and real-time inspection. This task requires more in-process data, so the large amount of high-dimensional and high-volume raw sensor signals should be processed. To achieve real-time inspection for this high-speed process, feature recognition should be done in a short time interval with sufficient accuracy and low computational load. It's not an easy task, especially when the targeting feature inside the data is inapparent. The third objective is combining the winding inspection framework with the contacting process. This is because to decide whether a coil is successful, some quality indexes are related to the parameters from both these two processes. In this process, some unpredictable influencing factors introducing the difficulties. In addition, the time effect due to tool wear is hard to quantify, and the material properties is influenced by the winding process. The current achievement could be summarized as follows. The first is develop a geometry fault inspection framework for the winding process based on image data. Then, this framework is improved by introducing the wear length data. These coil samples are made by hand, and the faults are introduced artificially. Because of the small amount of data, the inspection algorithm is expected to focus on the region of interest, so a background removal algorithm grab cut is applied. The resulting image is shown in this picture. The following data augmentation techniques are used to enlarge the dataset and improve the generalization ability. The classifier is a typical convolutional neural network, ResidueNet 50. There are two reasons why use it. The first one, this framework has shown a very good performance on image classifying. The second is we can use the pre-trained layers, which usually learn the low-level features. It is very helpful when our dataset is not large enough to train a network from raw. The final full connected layer is being modified. The number of the node has been reduced significantly, as our object only have three classes, and it is not complex. The accuracy of this classifier is around 80%. Furthermore, this classifier is extended. The wear length data is included, which means the length of the wear used in a coil. The wear length data of different classes could be mapped to a distribution. Then, once a wear length is recorded, the probability that it belongs to each classes could be calculated. The support vector machine is used as the final classifier. It can be seen that the accuracy is improved. The reason why the accuracy is slightly lower is that the poor quality data set is selected deliberately. In the future, the inspection framework will be further extended to multiple faults and real-time inspection. A deep learning-based framework will be developed to address the large amount, high-dimensional and different physical units data with sufficient resistance to noise. It is expected to have enough accuracy at a short time interval. Then the contacting process will be included. It is expected to make the time effect into account and capable to determine whether a coil is successful finally. Ignoring the mathematical process models, convolutional neural networks are used to learn the relationship between the multiple in-process data and product quality. For now, this framework mentioned above has been tested with the artificial data and will be tested on the winding machine in the lab. If the faults in the winding process can be detected during the manufacturing process, it could be a big improvement of the quality control for the EM productions. Thank you for listening.